Well, hello everybody, and welcome to Takeo After Dark. I don't know if it's dark where you are. I'm guessing in some places of the country this is more Takeo after lunch, but hey, it's Takeo After Dark as far as we here in the East Coast are concerned. My name's John Barba, and thank you all for joining us for this really special event and special series of presentations that we're doing in conjunction with Mechanical Hub. Mechanical Hub was so kind to invite us to participate and do this together. So we're really excited about being able to do that for you guys. On the line with me is Dave Holdorf and Rick Mayo, my co-trainers at Takeo. I think I just want to make sure everybody can see us, and we want to be able to share this information with you. Dave and Rick have both been, I've worked with both of them for decades, it seems, and through two different companies, and two of the finest professionals in the business. And they're follically challenged, as you may be able to see, but in each case, I don't know of anybody who knows more about hydronics than those two guys. So we're really lucky to have them. They'll be here with us throughout the series. And what we're going to do is during the presentation, I'll be delivering the presentation. And then after we're done, we'll stay on as long as you guys want to talk and ask questions. We're happy to do that. Okay. So before we get started, I just want to kick it to John Messenbrink of Mechanical Hub to kind of tell you how this came all about and just some specifics and some welcomes. So John, why don't you take it away for a sec?
Yeah, thanks, John. We really appreciate it. And we understand during this crazy time where people are sheltered in place, it's an opportunity for you guys to be in front of people. You guys are all across the country doing seminars and classrooms, and you're not able to do that anymore. So we thought it'd be a great idea to kind of bring this online where you can talk to people and do your trainings and seminars, and webinar in this case, to our audience. And we think you guys are the best at what you do, and so we really appreciate this. And we're looking forward to almost 8 weeks of doing these presentations. So thank you again, Dave, John, and Rick. We really appreciate it.
Oh, our pleasure. Thank you. Thank you. Now, before we get started, I just want to do a couple of housekeeping things for you guys. First things first, we're going to be together for about an hour or so. It's going to be real easy on a web presentation like this to kind of drift in and out and check your phone and do all this other stuff. Do me a favor, resist that. If you can resist that temptation, and treat this like we were in a classroom together. Live, face to face. What you should have is a pencil and a piece of paper, or a pen and a pad of paper, or whatever in front of you, and take notes like you would if you were in a face to face class, face to face training program. That'll help you keep focused and stay steady and stay on task. The other thing is I want to make sure you guys can ask questions. So a couple things. What I'd like you to do is on your control panel, you should see a little cartoon balloon. All right, that's how you ask questions, and you type them in, and we'll see them on the other end. So if you could do that for me, just find that function, type in just hi, hello, how are you? Gosh, 3 handsome guys, or gosh, 1 handsome guy and 2 bald guys, whatever you want to say. I don't care. Just type that in just so I know that you know how to do all this stuff. So that's pretty good. I got a couple here. All right, some good ones. Excellent. Hi, hello, how are you? Very good, very good. As we go through the program, please ask questions as they come up for you. We're not going to hold all questions to the end. We'll take a break every couple of slides and invite some questions and chat around a little bit. And then, again, as we said, we'll stay on at the end of this program for as long as you guys want to hang out to ask questions about whatever you want to ask us questions about. If we know the answer, we'll tell you. If we don't, if we don't know the answer, we'll tell you that too. So without any further ado, I'm going to flip all the cards and let's get started with the very first edition of Takeo After Dark. Takeo After Dark, again, it's, if you have a smoking jacket, I think it would be appropriate to wear. Maybe you get a nice, red leather lounge chair like that, some cognac or something like that. I think that would be appropriate for the evening and for the series of events, because we are very sophisticated people. As we said in the intro video, the first session is what this is, guys, is this is our factory training class, or our day-long training class. that we'll do out in the field, we'll do at the factory, wherever. And what we've done is we've broken it up into 7 or 8 different chunks, and we're going to have different topics. And each topic is going to be a building block for the next week. So we're going to start at the foundation, if you will, here. If you're building a house, you got to pour the foundation first, right? Well, you got to dig the hole first, but then you got to pour the foundation. What we're going to do tonight is dig the hole and pour the foundation for a great hydronic system, okay? And one of the things we like to share with our folks during our training classes is that, yeah, you know what, there's going to be a little bit of math here. And the first math formula I do want to share with you is this one. It's called DD equals MR. Now, I don't know if you know about this math formula or not. There's a bunch of them out there, a bunch of math formulas, and there's a little bit of math in hydronics. It's a science, so it's math-based. Don't be afraid of the math, though, folks. It's pretty simple stuff. Addition, subtraction, multiplication, division. Stuff you mastered by the 5th or 6th grade, all right? There's no trigonometry or any of that nonsense in there. It's just basic addition, subtraction, multiplication, and division. But when people look at this thing and say, and I show them DD equals MR, this is the most common reaction I get from people is, what the heck is that? I've never heard of that before. What the heck is a DD and what the heck is an MR? Well, in our world, DD has a specific meaning. DD stands for diligent design. Ho ho, it's not really an arithmetic formula. It's a formula for helping you to think about things. Diligent design, whether you're replacing a boiler, whether you're installing a new system, all of these things are going to be math-based. They all start with a fundamental process of finding out the heat load. Just by a show of hands, there's also another little item here, a little hand, okay? And that's the thing that allows you to raise your hand. By a show of hands, how many of you actually do a heat loss calculation for a boiler replacement? Raise your hand if you do. I hope a lot of you do. All right, I see Adam Breen does. Very good. I see a few other names. Not too many other hands going up here, people. All right. Why would you want to do a heat load calculation for a boiler replacement? Don't you just swap out the boiler? You know, look at the tag on the boiler you're yanking out. Figure it worked for 40 years. Why screw with success? Put in the same for same and be done with it. Go home. Why make this a project? Well, when you swap out same for same on a boiler replacement, you're sure as heck not doing diligent design. What you're doing is you're assuming that the guy who put it in 40 years ago did the math so you wouldn't have to. You're also presuming that the guy 40 years ago not only did the math because you didn't, so you wouldn't have to, but you're also hoping that over that 40-year period, not a blessed thing has changed in that house. They haven't updated the windows. They haven't done any weather stripping. They haven't buttoned up the envelope or anything like that. Those are two pretty big assumptions that you're making. And when you do the math, you can stop the oversizing if that is in fact a problem. And we all know, guys, that it is. To stop the oversizing, you got to do diligent design. And when you do diligent design, you get the MR. What is the MR? The MR is maximum return. DD equals MR. Diligent design equals maximum return. Like anything in life, gang, the more you put into it, the more you get out of it. All right. And I get that the real world's the real world. Everybody's got a lot of stuff to do. And the most important job isn't the one you're working on, it's the next one, right? But taking the time to making sure everything is sized appropriately and selected for a purpose, all right? Selected for a purpose, there we go, it's late here too. Selected for a purpose, then you're gonna get the best result possible. It's not that, when you start to make assumptions, like, well, I'm going to use this boiler because it's the same as the old one and it'll work. I'm going to use this pump because it's the pump I always use. I'm going to size the pipe at 1 1/4 because I know that's going to work, yada, yada, yada. Yes, it does save time. But as we oversize, we create problem after problem after problem. And none of those problems, friends, result in a system that's not going to deliver heat. A lot of times we take a look at our jobs and we say, well, nobody's freezing to death and blaming me. It must work. Well, sure, it works, but is it right? All right. Saying, hey, I put this in, it's working, nobody's freezing to death and blaming me. If that's the only hurdle you guys are looking at, to me, that's the result. That's basically the same thing as going through 4 years of high school with a D- grade point average. All right. After 4 years, if you pull a D- in every single class you take for 4 years, after 4 years of high school, What do you get at the end? Well, you get a diploma. You pass the bare minimum requirements. Ain't nobody bragging about it, all right? Your party at home with your parents isn't going to be that great, but hey, you passed and you're out. Good luck. Go get them. I got to believe anybody who is tuned into this webinar and who follows Mechanical Hub, you do strive for better, right? I can't believe there's a person in this audience that on your first day in the job, way back when, you said, boy, oh boy, I'm excited. I got a new uniform. I got a new toolkit. I got brand new tools. I'm so excited. I'm going to get in the truck. I'm going to go and I'm going to learn my trade. I'm going to work really hard. So someday, God willing, I'm going to barely not suck at this. All right. I don't think anybody had that mindset. We all strive for better. The real world tends to beat you down a little bit, but it's good to take that step back, think about what you're doing, and realize the more you put into this ahead of time, the more you're going to get out of it at the end, and the better it's going to be for your customers. So what do we mean by diligent design? Do the freaking math, gang. Math's not hard, all right? The math's not hard. And you may not do it, you may have it done for you, and that's okay. But just understand there's math involved and respect what those numbers tell you. First step in math that we're going to look at tonight is heat loss calculations. How do I know how many BTUs I got to stick into this house? How many BTUs does this house need? If I have existing radiation and it's oversized, what does that mean to me? What can I do? How can I take advantage of that? All of that comes from heat loss calculations. If you're replacing a boiler or putting in a big remodel or rehab, knowing the heat load allows you to size the pipe properly. Now, I'm no genius or no expert, but I know 1-inch pipe is less expensive than 1.25 and 1.5 pipe. 1-inch pipe is 1-inch fittings less expensive than 1.5 and 1.25 fittings. 1-inch air separators wicked less expensive than 1.25 and 1.5. By doing the math, you'll know whether you need 1-inch or whether you should go up to 1.25. That's all math. And knowing all of this, knowing the heating load and sizing the pipe properly, gang, then and only then can we get down to the serious business of selecting the circulator properly. And no, my friends, there's no such thing as one circulator is the only one you'll ever need because it has 3 speeds. That's a fairy tale. And no, my friends, there's no such thing as, hey, just stick a variable speed circulator on it, push the button, it'll figure it out. That's another fairy tale. It doesn't work that way. All right. We're going to show you how all of these things work when we get into our discussions on variable speed circulators. It's my hope we'll share with you some stuff that'll be exciting for you and a little bit different. But all of this stuff comes from diligent design. Ultimately, what we're talking about, friends, is installing a system as opposed to a collection of parts. Let me suggest this to you. It does not take a particularly impressive skill set for someone to install a bunch of parts, get a boiler, get some pumps, get some pipe, get some heat emitters, slap them all together, keep the water on the inside, light it on fire, and keep people from freezing to death. That's not that hard to do. A reasonably competent handyman could pull that off. Not even a highly skilled handyman, a reasonably competent one could pull that off. A system, however, is done by a professional. A system, when you install a system, every piece, every product, every part, every hunk of pipe is purpose chosen for that specific job. A system, by definition, is when the whole is greater than the sum of the parts. That's why we have our company names on our shirts and we drive vans with the company name on them. We're professionals. People expect more. We need to deliver more. That's what we mean by diligent design. The maximum return, well, it should be obvious. There's that intangible of knowing that the job's been done right, and you can pat yourself on the back for that. But there are some tangibles. You can control your material and labor costs, as we discussed. You deliver a system that has the efficiency as advertised, not just a combustion efficiency, but true system efficiency. If everything is sized properly, you're not over pumping to a terrible degree, the pipe is sized properly, the boiler sized properly, you have a greater system efficiency, and all of that should lead to better systems and the rewards that follow. So that's the maximum return. That's the soapbox part of the presentation. Diligent design equals maximum return. Simply put, do the freaking math, guys. That's the way it is. So let's get started with DD. DD, again, begins with a heat loss analysis. Now, there's a lot of different ways of doing heat loss out there. There's the manual J, and I'll pause while everyone says a novena, because manual J was given to us, by greater powers, clearly, because that's just the way manual J is. Manual J, I learned by doing IBR heat loss back in 1988. I learned how to do heat loss the old-fashioned way with a calculator, a pencil, and a pad of paper. Here's the thing about heat loss. There's a lot of different ways to do it, and everybody has their own apps or their own software that'll do it. Here's the thing. They all use the same arithmetic. It's the same math formula. Different models use different assumptions. They all use assumptions, however. Different ones use different assumptions, but they all use the same two math formulas that we'll show you. And that's as simple as it gets, the same two math formulas. And what those math formulas measure is infiltration, which is air leakage. Heated air leaks from inside to outside. It's replaced by cold outside air. We have to heat that up. And then there's conduction, heat loss via conduction, energy transferring from a warm surface inside to a cooler surface outside, through walls, through windows, floors, ceilings, doors, etc. We're going to show you how to do both of those things. At best, folks, heat loss is an educated estimation. We have to build in a lot of assumptions. In reality, I think everybody here knows the only way to do a real infiltration load, the only way to know a real infiltration load is to do a blower door test. But if the house is under construction, you really can't do that, right? And if you don't have a blower door, you can't really do that for a boiler replacement. So you have to do what we call an educated estimation. So let's get started. Before we take a jump in there, I just want to go back to Dave Holdorf. Dave, do we have any questions out there? Or are we still in the preamble stage?
Unfortunately, I have no view of the questions, John.
Oh, well,
so none of the panelists can see them at the moment. So I've been trying to figure out where it is.
Oh, okay. Well, then I have them right here, and I'm going to say, look at these things. I got howdy from Spokane. Now we're still all in the hello parts here, so that's all right. So no questions here yet, so that's okay. All right, well, let's get into heat loss 101. All right. For heat loss 101, again, as we said, all of them use the exact same math, air infiltration and heat transmission, and it is an educated estimation. Some terminology I want you to understand here. First is ODT, that's outdoor design temperature, the quote unquote coldest day of the year. Now, a lot of people have their local custom, their local standard, and then there's the ASHRAE published number, which you'll find actually in your handout section of your control panel. You should be able to download a nice PDF file that has all of the information we're going to share with you, including outdoor design temperatures for all over the US and Canada. So outdoor design temperature is your quote unquote coldest day of the year. People who look up the ASHRAE numbers are often surprised at how high the number is for their given area. I've had guys look at the ASHRAE number I lived in Minnesota for 22 years. The ASHRAE number there, I think, is like 12 below. I said, oh my God, it gets colder than 12 below here. We can't use that number. We got to put out what it really is. And that's cool. That makes some sense. But understand this, the ASHRAE number for a given area is based upon the 97.5th percentile of outdoor temperature over a given period of time. What does that mean? That means over a given period of time, going back 20, 30, 40, 50 years, what they're saying is, you know what? It doesn't get any colder than this 97.5% of the time. All right. 2.5% of the time it does, but 97.5% of the time it doesn't. And if you do a heat loss to that 97.5 percentile number, you should be fine 97.5% of the time. Then guys freak out. Well, what about that 2.5% of the time? They're going to be upset. They're going to be cold. They're going to call me. It's going to be my fault. I'm going to exaggerate this number. I'm going to go, instead of minus 12, I'm going to go to minus 25 because it hit minus 25 a few years ago. You can do that. You got to do what you got to do to sleep at night. That's understandable. But understand, the more you do that, the more fudge you're adding. There's so much fudge in these numbers as is. It's a wonder we're not all diabetic. But the more fudge you put in, simply the more sweetness there is, and the more you're oversizing. All right, for those one or two instances. And here's another thing to think about. Let's say you do a heat loss at that 97.5 percentile number, and it comes out to 57,421 BTUs for your house. What are the odds, folks, of you A, finding and then B, installing a boiler with an absolute net rated output of 57,421 BTUs and not a drop more? I'd say those chances are slim and none. You're going to pick the brand of boiler you like, size up that covers it. Well, what if the brand of boiler you like, size up that covers it, has a net rated output of 75,000 BTUs? 57, 75. I got about 23,000 BTUs sitting around looking for something to do under design conditions. You're fine. It's not a dramatically oversized boiler given what sizes we have available today. So don't get too worried about it, all right? Don't get too worried about, oh, I got to exaggerate that outdoor design temperature. That's just something to think about on your end. So the next thing is IDT, which is the opposite. It's indoor design temperature. What temperature do you want to maintain indoors when it is the ODT outdoors? All right. Typically that's 70 degrees. Some radiant companies might say you use 65 or 68 because radiant's different. We're going to use 70 as our target temperature, indoor design temperature for our purposes today. And then there's DTD. DTD stands for design temperature difference. Design temperature difference. It's simply IDT minus ODT. Your indoor design temperature minus the outdoor design temperature gives you the design temperature difference. It's the difference between what you want indoors on that quote unquote coldest day of the year outdoors. What DTD will become is a multiplier. It'll become a multiplier, which you will see. All righty. Another term is U value. UV stands for U value. U value. When we talk about windows, we talk about windows we talk to us in UV, but we want to know the U value of any surface, any flat surface. And what UV is, it's an ability, it's a measure of a material's ability to transfer heat from one side to the other. It's a measure of a material's ability to transfer heat. Now in construction, we want really low U values, right? We want low U values. When it's cold outside, we want to keep the heat inside, right? And when it's hot outside, we want to keep the heat outside. So we want relatively low U values. We do not want to conduct heat from one side to the other very well. So there's some terminology to work with. And let's start with a quick example. And I've got a couple of questions here that I did see come up. Isn't the ASHRAE standard design temperature an average of the previous 5 years of data? There's been data in there, and that's Jim Hillpiper. How you doing there, Jim? Yeah, I'm not sure if it's a 5-year. I don't know if Dave or Rick can answer that specifically. It's over a set period of time beforehand. What I've seen in like the IBR catalogs, those numbers haven't changed since 1988. Okay, I'm not sure how software gets updated or does. Dave or Rick, do you have any information on that or any input on that?
Unmuting. No, I'm unsure how many years cumulative it is. I'm unsure as well.
Okay, terrific. Well, thanks, guys, and thank you, Jim. Glad to see you. Is it better to undersize or oversize? Says Jason Hodgson. Boy, that's a good question. It depends on how much of a gambler you are. I know of a guy who will routinely undersize his boilers if the heating system is zoned. All right, knowing that, hey, I can just turn down this one zone. I'll have enough heat over here for this other zone, or turn these two down. I have enough heat over here. And he plays kind of a shell game with the BTUs. And that's cool if you're a riverboat gambler. If that kind of works for you, yeah, that's fine. Me, I'm a little more conservative. I personally wouldn't do that, but it depends on how much of a gambler you are. Undersizing, you do have a tendency to maximize run times on the colder days of the year, and that has a benefit as well. So it just depends on how you look at things. To me, I'd rather have a little bit more just because I don't want to be too less. I know if they have all these things run at the same time on that one weird day, you don't want the phone call. But are you a gambler or not? That's really, I think that's a great question, and it's an individual answer. All right. With combination boilers, you always size to the domestic water. Well, I think with a combi boiler, yeah, you're going to have to. You're definitely going to have to. With indirects, we can play around a little bit, and that'll be something we discuss later on. When sizing a boiler, do you use output or net IBR output? Asked Steve Whelan, and somehow I know, Steve, you know the answer to this, but we were going to be discussing that actually next time. What's the difference between those two? I think that's a good question. We're going to hang on to that. Aaron Stotko, how you doing, Aaron? I believe it comes from ASHRAE standards, 169 rolling average from the last 30 years. Okay, well, that's real interesting. All righty, let's continue. Thanks for the questions, guys. That is awesome. Let's do a quick example. We're going to do this little room right here. And this little room right here is a teeny weeny room. It's 15 by 20 with 9-foot high ceilings. 15 by 20 with 9-foot high ceilings. Our indoor design temperature is 70 degrees, and we're going to use an outdoor design temperature here of 0. So Our DDT obviously is going to be 70 minus 0 for a design temperature difference of 70. The next thing we're going to need to do is determine our infiltration factor. Now, in that handout that you can download in the handout section, there is a full page of infiltration factors provided by IBR, which again is where I learned this. Now it's known as AHRI. And there are three different sets of numbers for three different types of construction. The first set is the largest numbers. Those are for your old farmhouses, houses that aren't very well insulated, really old structures, and they're going to be higher than the numbers you're looking at here. The one in the middle, the numbers you're looking at here, this is for anything post-1978 construction codes, and really anything built from the mid-70s on, normal residential construction, 2x4 to 2x6 construction, depending upon where you are, regular insulation, etc. Again, it's a estimation, and there's a lot of estimations here in our world. And then the third set are for those super duper tight houses that you can't even breathe in, okay? And those are going to be lower than these numbers. You choose your infiltration factor based on how many outside walls have openings. It's not how many outside walls you have. It's not how many openings you have. It's how many outside walls have an opening. All right. If I have one outside wall with openings, which just by looking at the room we're looking at here, there's two windows in that one wall. We know that's the answer. It has one outside wall with openings. I would use a number of 0.02. And what that represents is 2/3 of an air change per hour. Two outside walls with openings, that reflects one air change per hour. The number we're going to use is 0.018. And three outside walls with openings, or the main in and out, the main entryway of the house, 1.5 air changes per hour, we're going to use 0.027. Now, what do these numbers mean and where do they come from? That's a really good question. Let's take a look at our next slide and I'll show you what those numbers mean. Let's say we have a real little room, okay? A little room for little miniature Oompa Loompas, maybe 1 foot by 1 foot by 1 foot. How many cubic feet of air do we have inside that room? We have 1 cubic foot of air, right? Length times width times height gives you the volume of a cube. So 1 times 1 times 1, that's 1 cubic foot of air. Now, I've got one outside wall with openings, okay? That one outside wall with openings, that's the infiltration wall. That's where I'm going to have my air leakage, so to speak. That's my air leakage wall. Now, let's say it's 70 degrees indoors and 70 degrees outdoors. At that point, I'm at equilibrium. I have no heat loss, all right? But now let's have it drop the temperature outside, drop to 69 degrees. Now, technically, I have a heat loss. Now, IBR built some test houses with the University of Chicago many, many years ago, and they tested air leakage rates. And what they found was, and again, this is a generalization, what they found was a room with one outside wall with an opening, okay, will have 2/3 of an air change per hour. So what that means is in this room, 2/3 of a cubic foot of 70-degree air is going to leak from inside to outside over the course of an hour. And the same amount of air, 2/3 of a cubic foot of 69-degree air, is going to leak back in. It's going to go from outside to inside to replace it. I'm going to need 0.012 BTUs to raise that 2/3 of a cubic foot of air 1 degree. All right, that's what those factors mean. That's where they come from. They're BTUs that are needed to raise a certain amount of cubic feet of air 1 degree Fahrenheit in 1 hour. So that's why we're going to use 0.012, and that's what the number means. So let's measure our infiltration for this room. It's 20 by 15 by 9. All right, here is your infiltration heat loss math formula. And it's all multiplication. This is one of the ways math is really cool. When you're multiplying, you just do it in a string. It doesn't matter what order, you just do it in a string. In this case, length times width times height times your design temperature difference times your infiltration factor will give you your infiltration BTU load. So let's fill in the blanks. And if you got a calculator, gotta play along at home, gang. 15 times 20 times 9 times 70, that's our design temperature difference, times the INFAC of 0.012, multiply that out in a string, and that will give us an infiltration heat loss of 2,268 BTUs under design conditions. All right, so that's infiltration heat loss. Let me check and see if we have any questions there. Let's see. Boom, 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 boom. Okay, is there a problem? I'm not free, just a still picture. Is anybody else having a still picture out there? Let me know. I'm not sure if that's just Alan or if that's everybody else. And if I'm sitting here talking to myself, let me know. Let me know.
I'm hearing you just fine.
Okay, very good.
You
Okay,
did
Alan,
seem to freeze up a little bit there, John.
it
But
did seem
I
to
think
freeze
it's all,
up.
yeah, I think you're all right now.
Okay.
Not out west.
Okay, there we go. For determining DTD, do you have to use all temps in Fahrenheit? Question coming from a metric Canadian. I'm not sure. I've never done a heat loss in Canada, although you can use Fahrenheit. All right. It's just math to find BTUs. All right. So I would say use use Fahrenheit. It's just to find BTUs, and then they can set the thermostat to whatever the Celsius equivalent is. So I would use it just because of the factors that I know, of the math formulas that I know, they're all in Fahrenheit. So
Here's
that's
the
kind of how I would do it.
well, here's the other reason, John, that you want to keep it in Fahrenheit is because a BTU is the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit.
Yes,
So
that's true. Very good. Good point. Good point, Dave. That's why, see, guys, this is why Dave and Rick come with me everywhere. They make me look smart, or they make me look dumb. One of the two. I'm not sure which it is. They've done both on occasion. All righty, let us continue up. I got one more question here. If you were to design this room for AC and the ODT is 95, IDT is 75, DTD is 20, the INFAC will remain 0.012. I'm gonna refrain from answering that because I'm not a heat gain guy. Rick or Dave, if you've done heat gain analysis, if you guys could answer that question. We're just working on heat loss here. So we'll take a look at that as we move along here. But yeah, we'll see if we can come up with an answer for you in terms of heat gain, because it's a little bit different. I mean, it's the same. Heat gain is typically the same thing, only different, if you know what I mean. All right, let's take a look at windows now. We've done the infiltration. Now let's take a look at the windows. For window loss, now we're just talking about conduction, and we're not worried about volume of air. We're not worried about leakage. We're just worried about conduction. All right. So now it's length times width times design temperature difference. Length times width is area, okay? Length times width is area times design temperature difference times the U value of the window. Now, we talked about U value a little bit earlier. It's the ability of a material to conduct heat, all right? So when we're talking about U values for windows and for wall assemblies or whatever, we don't want a big U value. We want a little U value. We don't want to conduct heat very well from one side to the other. With windows, you're fairly lucky. The U values are either, sometimes if you're doing new construction and you have a full set of plans, you go to the back page, the general notes section under the fenestration schedule. They'll tell you what the U value of the window is by specification. If you know the manufacturer, you can look it up on their websites, or you can look at what your eyes tell you. You can look at what your eyes tell you. When it comes to U value, understand that U value is the flip side of R value. They're like kissing cousins almost. If you know the U value of something, you can find the R value. If you know the R value, you can find the U value, because they are flip sides of the same coin. They're the inverse of one another. So let's say you knew the R value of something, and this will become important when we talk about walls. 1 divided by R equals U. 1 divided by R equals U. If you know the U value and you want to find the R value, then 1 divided by U equals R. So 1 divided by R equals U, 1 divided by U equals R. So that's kind of how you can use that formula to your advantage, just as long as you know how to do that. 1 divided by R equals U, 1 divided by U equals R. You'll be able to get some good information later on. For our purposes, and in that little handout, you're going to have a list of every window you could possibly imagine and their corresponding U values. It's a great resource. That's why we gave it to you. But keep this one in mind. Your industry standard double pane, low E, wood or vinyl frame window, kind of a standard, regular, everyday window, all right, is going to have an R value of about 2.77 and a U value of 0.36. R value 2.77, U value 0.36. All right, so that's what we're going to use here. Now let's take a look at our windows. We have 2 windows. Each window is 3 by 5. 3 by 5, length times width, 3 by 5 is 15 square feet. So I have 2 windows, each one's 15 square feet. Now I could do this math twice, once for each window add them together, and I got a number, right? Or I could simply add the area of each window together. 15 square feet plus 15 square feet is 30 square feet. As long as they're the same basic window, the same type of window, I'm going to come up with the same answer. So let's make this a little bit easier on ourselves. All right. Remember, gang, we're not flying this thing to the moon. All right. It's a house. We're trying to replace heat. We don't have to get too crazy about this. 30, call it 30 square feet, and we're going to call it good. All right. 30 square feet is going to work. It's a house. It's not a rocket ship. So in this case, what we can do is 30 square feet times 70-degree design temperature difference times a 0.36 U value. That's going to give me a BTU load for my windows of 756. Okay, 756 BTUs through the windows. All right, so that's kind of where we're sitting right now. We've got our infiltration, we've got our windows. Next step is going to be the walls. All right, I'm going to do the walls, and then we'll take another look at the questions. Outside walls, we want to do the heat load for outside. Well, obviously, we don't care about the inside walls, because on the inside walls, on the other side of the inside walls, another heated room, there's not going to be any heat loss there. We're looking at outside walls. According to this, our room has 2 outside walls. One of them's 20 foot long, and one of them's 15 foot long. Our formula for walls is length times width. It's area, but in this case, we're going to be talking about net area. So basically taking out everything we've already done. In this case, it'll be the windows. If there were doors, we'd take the door area out. All of that be taken out. So it's net area times design temperature difference times the U value of the wall assembly. Now let's take a look at this. We've got 2 outside walls. One of them's 20 foot long, one of them's 15 foot long. Make our lives a little bit easier. Let's just presume this to be one long wall. 20 foot plus 15 foot, that's 35 feet worth of outside wall. Again, keep it simple. Make it one big long outside wall. 35 feet times 9 foot tall, that's giving me 315 square foot of outside wall area, gross wall area. Now from that, we're going to have to subtract the window area of 30 square feet. So we subtract the window area of 30 square feet, 315 square feet minus 30, that equals 285 square feet. That's the net wall area. Next, we want to find the U value. And in this case, unless you have X-ray vision or the customer gives you free rein with a Sawzall, you really don't know what's in there. So you're going to have to use your experience. Where is this house? What are other houses in the neighborhood like? Is it 2x6 construction? Is it 2x4 construction? What do we have for insulation in the wall is generally the best bet. For this example, let's say it's R19, 6 inches of fiberglass. All right, I know there's other stuff here. We'll round up to get it, but let's take a look at the biggest structure there, and that's the fiberglass. 1 divided by 19, which is the R value, 1 divided by R equals U. So in this case, 1 divided by 19 equals 0.05. We'll round up 0.05. We'll call that good. This is a nice little piece of fudge if you're looking for some right here, okay? I know there's studs. I know there's other stuff involved. Again, not flying it to the moon, just trying to heat it up, okay? So in this case, 285 square feet, our net wall area, times 70 degrees design temperature difference, times 0.05, our U value, that gives us a wall load of 998 BTUs. All right. Now, have we forgotten something here with walls? Are we concerned about which way are they facing? Are we concerned about orientation, north, south, east, west? Is that something we need to be concerned about for heat loss? Well, the answer to that is no. Heat gain, yes. Heat gain, yes, you do need to be concerned about it. But heat loss, no, because when is it usually coldest out? That would be at night. And at night, most places, it's dark, all right? And the house doesn't know what direction it's facing. It can't see. So we don't need to take north, south, east, west into account. Another factor here is there is no known math calculation for lunar gain, okay? So as far as we're concerned, the orientation of the house for heat loss is insignificant, so we don't have to take orientation into account. All righty, very good, very good. I'm going to go back here and take a quick look at some other questions. Okay, where do I get the handout? The handout on your control panel, there should be a tab there for about 2/3 of the way down, 3/4 of the way down. It says handouts, and you can download that PDF right from there. Okay, very good, very good. Let's see what else we have. Boom, 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 boom. Okay, okay. Do, 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 do. There are three simple rates. Old farmhouse after 70s very tight, or is that to determine the infiltration factor? Asked Derek. Yes, that's how we determine the infiltration factor based on the type of construction. If you use software, you can look at different people's software that have the heat loss software. They ask you, is the house tight, semi-tight, or loose? That's the same thing. It's just how they will calculate infiltration based on that simple checklist. So there's no voodoo here or magic. It's just you have to make certain assumptions. One thing about infiltration, I only go back to that. One thing about infiltration, a lot of people will say, well, what about wind? Do we have to take wind into account? Well, yeah, wind has to be taken into account, but in this case, no, you don't have to do it. Again, we talked about these infiltration factors. Again, these were all developed by IBR in conjunction with the University of Chicago years ago. And they had to make some assumptions. And one of the assumptions they made was that there would be a 25-mile-an-hour wind blowing in all four directions at the same time. A, I'm not sure how that could possibly happen. And B, if it did, I don't know which way your hair would blow. Rick and Dave, don't worry about it. But hey, it's what you got. That's the number. All right. So when I talk about fudge factor being built in, Glorioski, there's a ton of it right there. Okay. Yeah, there was a question right here. Alan Peters asked, what about wind? There you go. Well, now you know. Okay. This is the heat loss formula, so it can be used for hot air and hydronics, correct? Yes, it's a heat loss formula. Absolutely. Absolutely. All right, good. Great questions, guys. Thank you, thank you, thank you for the questions. Let's keep moving on. Let's talk about ceilings and let's talk about floors. Okay, oh, we did outside walls here. Let's talk about ceilings and let's talk about floors, shall we? Ceilings and floors, same math formula, right? Length times width times DTD times U value. Length, width, DTD, and U value, same as before. There are certain circumstances when you'll do a ceiling loss and certain circumstances when you're going to do a floor loss. They're not part of every math equation, every room equation. Ceiling, of course, you do only if there's no heated space above. All right. So if you've got a first floor and there's a heated second floor above, well, skip this step. You're not going to have heat loss through the ceiling. There's a heated space above. If you have a cold attic, all right, well then yeah, you're going to have to do a ceiling loss. And there's you look up in the handout, you'll find a formula or a U value for an attic assembly. If you have a built-up roof / ceiling, so on one side is inside and the other side of the ceiling is the roof, the other side of the roof is outside. Well, yeah, of course you got a cold lid, you got to do a heat loss then for the ceiling. For our purposes, for our example, we're presuming a heated space above, but the math is the same: length, width, DTD, U value. If you're in a situation where, say, half of the ceiling has a heated space above it and half of it doesn't, well, then you only figure heat loss for the half that doesn't, quite obviously. So that's kind of how you would approach a ceiling. Okay, ceilings only if there's no heated space above. Floors are kind of weird, they're similar but different if it's a heated space below, right? So if you're on the second floor and there's a heated first floor below you, well, skip this step. There's no floor loss, all right? If you're over an unheated or unconditioned basement or an enclosed crawl space that's kind of like a mini basement, all right? Same idea. IBR says, no, you really don't have to do a floor loss in that instance. Because if you think about it, in a basement, it's not 0 degrees in the basement, right? It's more like a constant 55 or thereabouts. If you were to do a heat load through the floor of 70 here and 55 there, that's a design temperature difference of 15 degrees. If you did that math, the number would come out so low that it would be more than offset by a person walking into a room. Remember, your body with clothes on loses about 400 BTUs per hour when you're at rest or at light activity. So in that instance, they say, no, you know what? You don't need to do a floor loss in those two instances, simply because it's not 0 degrees down there. Do what you got to do to sleep at night, people. I'm not going to nitpick, but just use some common sense when making that decision. If you're over an open crawl space, a ventilated crawl space where the temperature in that crawl space is similar to or close to the temperature outdoors, well then yes, obviously you must do a floor load then. If it's a slab on or below grade, you must do a floor load then. Again, that handout will show you how to do that. So in our example, we're going to presume we're over an unheated basement. So there's no need to do a ceiling loss for this room. There's no need to do a floor loss for this room. That tells us we're done with this room. All right. So let's go back to the job. Let's total it all up. I've got infiltration heat loss of 2,268. I've got windows of 756. I've got walls of 998. That means for this room, we're talking about 4,022 BTUs. That's the, and BTUH/R, that's BTUs per hour required. BTUs per hour required. That's what we need to deliver to that room under design conditions to keep it at 70 degrees. All right. Now, is that number kind of bloated? Is that number exaggerated? I bet you most of my money and all of Dave Holdorf's money that yes, it is in fact higher than reality. Because again, we estimated the infiltration on the high side. We took some liberties with the U value on the wall. All right. There's so much fudge built into these numbers by themselves that we really don't have to add any extra. So I'm pretty confident that that room has a BTU load, you know, less than 4,000 BTUs. But this is what we calculated. Okay, this is what we calculated. So it goes back to that question someone had earlier about undersizing a boiler. You know, if I had a BTU load of say 70,000 and I had a boiler that had an output of 68,000, would I be okay using that boiler? Yeah, probably. That might be one of those ones where, you know, I think that might be close. Or 69,000 and 70,000. Yeah, you know, that might work okay. It's the same thing when sizing a circulator. If your flow and head requirement is just a wee bit above a fixed pump curve, would that pump be okay? Yeah, probably just fine. Because again, we have exaggerated the heat load here just a little bit by math, by estimating, and that's just the way it goes. Now let's quick do the rest of the house. Hey, look at that. How quick that was, 78,379 BTUs for a total BTU requirement for this sample house that we're doing of 82,401 BTUs per hour required. 82,401 BTUs per hour required. I would suggest to you that that is a big freaking house, okay? That's a really good size shack. So in that instance, this is gonna be, and I got to tell you, the reason I say that is I lived in Minnesota for 22 years, and we had a 2,400 square foot house that was built in 1978. The coolest thing we did to it was they upgraded the windows in the late 90s. All right, it was 2x6 construction. It wasn't a fancy house. It wasn't a super tight house. It wasn't a crazy well built house. All right, it was just a good solid house. When I did the heat loss calculation by the book, I came up with 44,000 BTUs for this shack. 44,000 BTUs, and I used a outdoor design temperature of 15 below. All right, so imagine how big this house is. A lot of times when guys do heat loss and they want to do that shortcut, a lot of times guys have their favorite multiplier. Well, I'll just figure 30 BTUs per square foot and call it good. Man, that's going to, and they say, well, it works. I didn't underheat. It works. I sized the boiler right. The boiler works. I always think about that. He says, yeah, but that's kind of like doing finished carpentry with a sledgehammer, man. You know, you could do finished carpentry with a sledgehammer and it'll work. I mean, the nail's going to hold them two pieces of wood together, but the end result's not going to be pretty, right? It's not a professional job. I get that it's faster. I get that it's easier. I get that it's close enough, but no, it's not really close enough. It's close enough like, you know, a nuclear weapon is close enough. You know, I think we can be a little more targeted than that as professionals, can't we? So I remember that, and I always share this one example in our training classes. In Massachusetts, where I grew up and learned the business, Interstate 90, the Massachusetts Turnpike, cuts Massachusetts in half the long way. It goes from Boston to Stockbridge, Massachusetts. Or if you're a fan of James Taylor, from Stockbridge to Boston, the highway goes both directions. But it cuts Massachusetts in half the long way. To this day, there are people who swear up and down that if the house is built north of Interstate 90, you figure 30 BTUs per square foot. But if the house is south of Interstate 90, because we all know the further south you go, the warmer it gets. If the house is built south of Interstate 90, you only use 20 BTUs per square foot. But nobody has yet been able to explain to me why moving a house to the other side of Interstate 90 automatically increases its heat load by 50%. I don't get that one. You know, I abused a lot of different substances back in my youth, but not that much. All right, not that much. I get that it's quick. I get that it's easy, but it's also not. It's that's what a handyman will do. I think a professional, when they have the tools available, whether it's knowing how to do it by hand or so many of the apps and so many of the software applications that are out there that allow you to do it accurately as long as you know what you're looking for. Oftentimes it takes longer to compile the information than it does to do the math. All right. So always think about that, even when it's a simple boiler replacement, because why perpetuate the oversizing? Why perpetuate the mistake for another generation or two? Get it right. That's what they pay us for. So next week, we're going to talk about delivering the BTUs. How do we deliver the BTUs? We're going to look at baseboard and the finer points of sizing baseboard. What all those numbers mean? What's that mumbo jumbo all about? We're going to talk about cast iron radiators and EDR, maybe a little bit about panel radiators, and maybe a little bit about radiant floor heating. How do you size that stuff based on the loads, and how do you know what you're going to get? How much do you need? What if I have existing baseboard and I got to replace the boiler, but they use that old-fashioned method of just lining the outside wall with baseboard? What do I do then? Well, that's a good thing. If you do the math, that could be a really good thing. So those are the kinds of things we're going to be talking about next week. All righty. So with that, I'm going to bring us all back here, and we have our guys on the. What did we lose, Rick? You might have had to go to supper. All righty. Some more questions here, guys. There he is. How you doing, Rick?
Evolving.
There we go. Let me know, guys, what you thought of this. How did we do? Let's take a look here. Boom, 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 boom. This formula works great for commercial buildings as well, as Jake Lowry. I think you would want to. I think you'd want for commercial. You're going to need a little bit more detail. That's why Manual J is this thick, and then the commercial addendums to Manual J are this thick, okay? Because it depends on the kind of commercial building you're using. There's always going to be a little bit more information, Jake, but the math formulas are the same too, man. The math formulas are the same too. In commercial buildings, you're going to be taking lighting into account. You're going to be taking, depending on how many people are there, you got to take that into account. So many other things, different types of equipment that might be in that building. A lot of those things need to be taken into account. But for heat load, for commercial building, it's the same two math formulas. All right. Let's see. Based upon the first room, that house would be 6,400 square feet. Yeah, if you're going with the BTU per square foot load, yeah. If not, yeah, we'll see. We'll see. Here's one from a gentleman named Todd Facey. I'm not sure if I'm familiar with Mr. Facey, but Mr. Facey has a very direct question. How does John feel about Tom Brady going to Tampa Bay? Well, after it took me a few days to stop weeping and get out of the fetal position, but I'm manning up now, and I'm going to go out buy my number 4 jersey and be part of Team Jared, man, because that's what we're doing. Yeah, it's time for Jared Stidham. All righty. Could we get a copy of your slideshow so we can follow along with your example? Jordan, actually, this is being recorded and will be archived on the Mechanical Hub's YouTube page. So you can follow along there. Slideshows we're not allowed to give out, unfortunately, but you can certainly follow along on the recording. And again, I urge you to download the handout. There's actually there's a sample job in the handout that you can do to do an entire whole house. So that's good. That's some good stuff there. So you could do that entire house sample if you wanted to. All righty, some more questions. Can we use this for multifamily apartments or condo buildings? I'd say a 2-family house, sure. That'll work just fine. Again, the more commercial this is, the more you have to take other things into account. But condos, sure, it's all heat loss. Absolutely. How do we count for ventilation rates? Rick, you have answered that question in such good ways that I always learn a little bit of something when you do that. And I guess we're talking about a heat recovery ventilator. Rick, could you take that one for me?
One thing that you can do, if you know the house is built relatively tight within certain code requirements that are established by the local, folks that are going to come and look at these jobs, you can assume that using about a third air exchange an hour would be considered tight. And within that third, you look at the efficiency of the HRV or the ERV, and you can actually slice that number down based on the efficiency of the ERV or HRV. So again, that's something that can be figured in there and just gets it dialed in a little bit tighter. So the HRV or the ERV actually recovers some of that energy. And so it's not like just bringing in that really cold air. You're bringing in that cold air, slightly raising it up through the heat exchange process. And now that's used in your favor. Again, John keeps talking about fudge. That'll give you some more fudge. So all the more reason not to exaggerate that infiltration rate.
Right. Yeah. I mean, yeah, you're mechanically controlling your rate of infiltration now. Yeah.
And recovering.
And recovery. Very good. Excellent. Excellent. I hope that answers your question, Brad. Does wall material matter when doing a heat loss? Block wall, drywall, paneling? Absolutely. Absolutely. That 0.05 we used was for standard 2x6 construction. And really, when you think about it, when you think about it, Jason, for your wall assembly, okay, you've got the sheetrock on the inside, then you've got the insulation, then you've got some poly in there somewhere. You've got the sheathing on the outside, you got the Tyvek house wrap, okay, and then you've got the shingles, and then you've got a cushion of air on the inside and a cushion of air on the outside. Now you can figure out the U values for each one, put them together, convert it to an R value, and bada bing, there you go. But then you also got to understand every 16 inches, you don't have that assembly. Every 16 inches, everything's the same, except instead of insulation, you got a hunk of wood. Then you got to figure out what that U value is, turn it into an R value. Then you got to figure out what percentage of the wall has the wood assembly, what percentage of the wall has the insulation assembly, and then do that all up, and we'll call it good. Now, different wall materials are going to have different U value assemblies. Again, that's why I'm going to point you to that handout, brother, because there's a list 1.5 miles long of virtually any kind of wall assembly you could imagine: brick, stucco, uninsulated, insulated, rock wool. My God, you'll learn more about rock wool insulation than any human being should know in 2020. You know, that's all that stuff's in there, and you just pick the one that best reflects what you're dealing with on this particular project. Speaking of apps, is there one that you would recommend for heat loss? Guys, what have you guys used? What's been your experience, both Rick and Dave?
There's a list of things. I know Dave and I both dealt with RightSoft for a while. Avneer makes most of the software for most of the tubing companies, I should say. Yeah, between those two is what I'm experienced with. I haven't had to mess with it in a few years now, but those are the two I know. How about you, Dave?
Yeah, I'm still back to the old Avenir style software, and I've been using the FlowPro design software too, obviously. You know, for a couple of things. I mean, I don't get like Rick, I'm not doing a lot of designs any longer. So I got a handful here and there just from guys that I know or family and whatnot. So, and I'll use the Takeo design software to get my heat loss numbers and to figure out baseboard lengths that are happening in some projects. But that's about it right now.
Right. I mean, Takeo does have a design software package on our website. There's a commercial one, and if you're doing skyscrapers, you can use that. But the FlowPro Designer, which I still believe is still on our website, you can download that. It's drawing based. It's a good heat loss software. I've also used the SlantFins heat loss app, which a lot of people seem to like. It's fairly simple. You plug in numbers, it'll give you a number back. But there are a lot of different ones out there. A lot of Radiant companies, a lot of them have their own different software heat loss programs as well. So I think any one of those could work. So there you go.
Yeah. In my experience, I remember going back quite a few years ago when everybody started blowing up with software. And I checked out 10 different softwares one day with a first floor of a house, and they were all within 5% of each other, the calculations that came in. So whatever you choose to use as software, just remember to trust the numbers. Believe what the numbers do when they spit them out to you. A lot of times they're going to be lower than you've expected, most often. So you'll see heat losses and you're not going to believe it. So, but just believe that number. We have, like John said, we have a lot of fudge built into this, doing it by hand. Once you really dial it in, that's when all of a sudden these numbers just start looking lower and lower and lower. And, don't be afraid of it. Do not be afraid of it, because you did the math. If you did the math, you can never, ever, ever be wrong.
Right. As long as you do the math right. There you go. We used to do a heat loss class at our factory many years ago, and I gave the guys a set of blueprints. All right. And So before you guys, all you guys, you've been in this business a long time. I want you to take your best estimate on what the heat load here is. And it was like a 2,000, maybe 2,200 square foot house. We picked Walla Walla, Washington, because it had a 7 degrees above zero outdoor design temperature, and I just really like saying Walla Walla, Washington. So we use that as the design area. And I told guys, just come up, what's your best guess? And guys would be thinking they'd actually be doing that quick little BTU per square foot kind of thing, yada, yada, yada. And we had guesses that ranged from a low of 50,000 BTUs to a high of 125,000 BTUs. These are all guys, professionals, been in the business a long time. This is what they guessed. This is what they guessed. I said, okay, cool. Now let's do the arithmetic. And we walked them through the math. They did all the calculations. And these guys, jaws hit the floor when they realized the actual heat load of that house was about 30,000 BTUs. One room needed 3 feet of baseboard, and this guy said, "It ain't gonna work. I can't do that. I can't put in 3 feet of baseboard. It won't work." I said, "You did the math. It said, no, I'm not gonna do it. I'm not. I said, okay, well, that's not, that's habit taking over science right there. But that's the way it is. You got to trust the numbers, as Dave said. You got to trust the numbers. So
On
what
the
do we
next
have?
episode,
Say again?
I said on the next episode, we'll get to see how that becomes good for us. That guy that wouldn't put 3 foot in there, but put 6,
Absolutely. You're right. You're right. Absolutely. Let's see what else we have. Where is that handout again? Asked Craig. Again, on your control panel. All right. If you look down just above the chat section, you should see something that says handouts 105. If you click on that little arrow that next to handouts, it'll explode down and you'll see the handout. And then you just click on that and download it. All right, and then you'll have it as a PDF once you open it up, you're going to love it. So it's got a lot of great information in there. Outdoor design temperatures, it has all the definitions, it has the infiltration factors, it has U values for everything that you could imagine, plus a step-by-step process, worksheets, everything, plus an order sheet so you can order more stuff from AHRI. So it's all in there. So that's pretty cool. So Dave Holdorf has the best hair in the HVAC industry. Okay, that's from Ken Watson. So Ken's taking some shots here because Ken,
Wow.
You people out there don't know this. Ken Watson has and I say this with all sincerity, a gorgeous head of hair. I envy the man his hair. I really do.
I don't think I've seen it move yet, though.
Yeah, it's weird. I was walking with him in a 30-mile-an-hour wind. That hair didn't move. Not even a little tuft going up. Nothing. It was like it was made of steel. It was coolest thing I ever saw. All right, that's Ken Watson. And I need a light for my Takeo banner. So always the branding guy, right? Always the branding guy. All right, can I give a shout out to my employees that showed up? I want them to know we appreciate them showing up for training, and thank you guys for taking the time to help us all. My pleasure. That was Adam Breen who said that. So if you're one of Adam Breen's guys, Adam's giving you a shout out. Okay. New codes require fresh air intake for kitchen hoods. This air is not mixed, is usually dumped into the return ductwork in the home. Not knowing how long this will run, how do we compensate for that? Another good question, guys. Dave's got a little chuckle here, so go ahead. Want to tackle that one?
Oh God, that's a challenge, man. I remember a couple of projects I designed way back in the day, and the engineer wanted it designed for 2 air changes an hour. And I said, but is it really going to run for an hour? And he's like, it could. I'm like, well, yeah, I could leave the door open too and still not heat my house. That is a challenge. At this point, it's going to depend upon on who's going to inspect, if anything, and what's happening, and just maybe add a little bit to it. I know in a lot of the softwares that you have out there, there's a selection if the room has a fireplace. And if it has a fireplace, it will change the air infiltration factor and go up just a little bit, just to thinking that you've got an open window. Same thing with the would be if you had a kitchen hood. So that's what I usually did. I click on that fireplace in the kitchen just so I increase my air changes per hour.
In bathrooms, and IBR requests that you add 20% to your calculations for bathrooms. Part of that has to do with the bathroom fan, and part of that has to do with what we call the wet and naked factor. Right? And when you're in a bathroom, a lot of times you're wet and naked. All right. And that extra 20% comes in mighty handy. I'll tell you what, because I don't know about you, but I've been both cold, wet and naked and warm, wet and naked in my lifetime. And I got to tell you, I don't mind telling you, I much prefer warm, wet and naked. All right. That's just it. So maybe that's too much information, but it is Wednesday night. It's
Yeah.
Takeo after dark, man. We're going to be we're going to be hitting all the bases. All right. So yeah, that I think those are two different ways of looking at it. Yeah. And how do you allow for that? It depends. I mean, and yeah, like Dave said, you could be running all the time. Yeah, then again, it could not. You could leave a window open all the time. You know, people do that. You don't know. You just don't know. Steve Feisenmayer, I hope I got that one right. How does the domestic factor into the load, your domestic hot water factor into the load? Great question. It's separate. Now your choice, your decision is, how do you size your boiler? Do you size the boiler for the domestic load? Do you size the boiler for the heating load? And then upsize your storage if it's an indirect. We're actually going to have an entire section later on in the presentations, probably 6th, 7th, maybe in line, on how to understand what your domestic, your indirect hot water tank is all about, how to figure out how to size it. What do you do if you need more storage and you size the boiler for the heating load and not the domestic load? What can you do to allow for that? So yeah, we're going to be talking all about that. So that's just a little more foreshadowing. All right, boy, a lot of questions, guys. This is awesome. I'm glad you're here. All righty. Slantfin Explorer, says Robert O'Brien. Yep, that's a pretty good one. Will you cover solar gain in a later episode? Probably not, Jordan, because again, we're just talking hydronics and heating here. So not so much on a cooling load, because we don't do cooling per se in hydronics. But we can certainly look at that. Stanley Bard, Stanley, how you doing, man? How you doing? Stanley uses ACCA's spreadsheet. Could you elaborate on that for me, Stanley? Just throw in another comment on what you use that for. Is that for the range hood? Okay. Jeff Brown says, how does the operation of clothes dryers, range hoods, and other appliances that vent to the outside figure in the heat loss? Same thing. As much as a little to a lot, to a little to maybe a little bit more than a little. Again, dryers, you got that hose there. That's going to be part of your infiltration. That's kind of assumed. Could they have a big effect on infiltration rate? Some, but again, remember how we're calculating infiltration. It's based on a 25-mile-an-hour wind blowing in all 4 directions at the same time. There's enough fudge in there for these little, I think, for these little things, I would think. And one thing you might want to consider is if you have a laundry room, that's a wall with an opening, right? You got to consider that a wall with an opening. If there's windows there already, well, then you're fine, you're covered. Okay. Is it a requirement to be a trainer for Takeo to be bald or losing your hair? No, but it's a good idea, Anthony.
Hey, let me speak to the whole dumping. Some of you who know me, I grew up in Alaska, and we dealt with a lot of cold air coming into the residence through things like big gin airs and range hoods and things like that. A lot of time, what'll happen there is you'll actually calculate a coil working off the boiler with some glycol, right? And you'll pre-warm that air so that when it does dump, it doesn't dump at 0 degrees or 25 below 0 or something. And then that's actually added to the boiler load, and you compensate for it that way. So you warm the air up so you're not feeling that really cold air actually coming in and dumping on that kitchen floor.
Very good. Do you still use your PEX to keep everyone awake? We're going back to the late 90s in Happy Valley or Apple Valley or wherever the heck that was. This is a guy who's been around a while. All right. No, I don't. I prefer to use much more subtle methods. I have voodoo capabilities, just so you know. There you go. Stephen, the
Just
handout
throw
icon.
pumps.
Say what? Yeah, we just throw pumps now. It's a little more, not quite as subtle, right? The handout icon is the one directly below the question icon. Yeah, Steve, it'll say handouts right there. Handouts 1 of 5, and that's the one. You just click on that, click on the arrow, it'll turn 90 degrees and it'll explode that little window for you. All right, Jim Hillpiper, my man, Jim. Crappy part in using some of the heat loss calculation programs if you have the options of loose, semi-loose, and tight as infiltration options. This presents some diligent design troubles when it comes to sizing a boiler. Should BTU output be on the edge? What I am getting is you recommend IBR over ASHRAE. The software, all software is doing is making assumptions, right? They're just making assumptions. When you put in, say, loose, all right, They may be using the same set of numbers that IBR is using for the really loose house. It could be the exact same set of numbers. We don't know. Probably fairly close. So that's just how they go about it. It's rather than say how many outside walls have out, they just get loose, semi-loose, and whatever. So yeah, it's part of that voodoo. You're right. It's part of that voodoo that belongs here. I'm more comfortable with IBR because I understand the terminology. Like I said, it's the way I was taught, and it's what I've used most of my career. So yeah, I'm not saying IBR over ASHRAE. It's just when software uses loose, semi-tight, or tight, it could very well be the same set of infiltration numbers, just applied behind the computer screen, and you never see them. That's one of the things that I'm fairly certain that happens out there. Would the stove compensate for the air change? You could certainly look at it that way, Steve. I would think so. Hey, we have a contractor from England. How are things over in England? I hope everybody's doing well over there. Here in England, most homes have fireplaces. Wondering how you would account for the air movement up and down the chimney if you were to need to take that into account. Again, most software has that little thing. Is there a fireplace in this room? You check that, and it'll calculate that for you. It simply adds an extra layer of infiltration. Guys, Dave and Rick, is that kind of how you usually handle this?
In the software, I do, yes.
Yeah.
Yes.
Okay, and that would be the best way to handle that. Again, in the IBR book, you'll actually find some math calculations for fireplaces. They'll tell you what to add for fireplaces, and for the brick around the fireplaces, because that changes the wall loss a little bit too.
Of course, from a building science standpoint, you'd want to probably not put fireplaces in your house.
Oh yeah. HERS Raiders and building science guys, they'll be all over that. Yeah. Don't put in a natural draft fireplace. Put in a direct draft gas-fired sealed combustion unit, and then that's much better. Yeah. All righty. Thanks, guys. Now I know who gets a gift card for showing up. All right. I want to work for Adam Breen, man. That's pretty cool. He's giving guys gift cards for showing up to training. Of course, we get paychecks for showing up for training, so I guess it works out well for us too. All righty. For the next 2 Wednesday nights, I'll be celebrating Passover, so I won't be able to join you live. So sorry, Zvi, that would be we'll miss you, but I understand that's a much more important thing to celebrate, and we will have them. The recordings will be on Mechanical Hub the day after. How would you be able to get the handouts? We'll see if we can figure that way out with Mechanical Hub on how to get handouts available as well. We'll probably just have one more handout for the rest of the presentations, and that'll be next week. So if anybody misses that, we'll figure out a way to make sure that you get those, that you do get those handouts. What about
I would also
global
make
warming?
sure
Oh, go ahead.
make sure you register for the next week's class, so this way you still get the email and the link when it goes up too.
Very good. Yeah, and Mechanical Hub will be sending out their newsletter tomorrow with the link for next week's. Very good. Very good. Excellent. All righty. Hey guys, I think we're running out of questions here. So John Messenbrink, if you're there, you want to jump on in and add any final thoughts or passing thoughts to our gang? We're down. We still have 111 out of the. I think we had about close to 140 live at our peak. So we're down to 112 now. Somebody just came back on. But Mr. Messenbrink, if you're there, come on, say hi.
Yeah, no, thanks again for doing this. And everyone who attended, this is a great turnout for the first one. And we look forward to doing this every Wednesday. It's a great educational webinar. You guys can't get in front of people face to face, and we know that's like the most effective means of learning, but this is the next best thing. So, we look forward to these every Wednesday night, and we appreciate John and Dave and Rick for jumping on, and we look forward to these every week. So thank you.
And what's even better, this is one of the few times you'll get all three of us together.
Yeah.
All right.
True.
The best looking of the three, and then the two smart guys. All right. That's how that works. But yeah, we really appreciate it. Thank you for joining us. And thanks for all the questions and the great interaction. That's what makes these things fun. It's different. It's different from being face to face, but we feel like we've connected with you guys as well. So we'll see y'all next week when we talk about how are we going to stick heat in there, and how we're going to figure out what boiler to use and what are all these different terms mean and stuff like that. So again, thank you all for coming, and we will see you next week.
Peace out. Stay safe.
Bye-bye.